Hello everyone, in this TRC tutorial number 22, we will see that a single and simple schematic amplifier can be split in two different schematics just by changing the ground voltage reference. This schematic uses an operational amplifier of gain A. The middle point of the resistor divider R1 and R2 is connected to the inverting input. The non-inverting input is connected to the node B, and R1 is attached to the node A. The input voltage Vin is placed between both node A and B. Now, if we decide to connect the ground to the node A, you will recognize immediately the non-inverting amplifier schematic you learned in school with the closed loop gain of 1 plus R2 over R1, with R1 equal R2 equal R. The K1 factor is 1 over 2 and the gain is 2. Now, if we decide to connect the ground to the node B, you will recognize immediately the inverting amplifier schematic you learned in school with the closed loop gain of minus R2 over R1, with R1 equal R2 equal R. The K1 and K2 factor are equal to 0.5 and the gain is minus 1. It is interesting to see that both schematics we learn in school as two different schematics can be seen as the same global schematic amplifier, just depending on the ground connection to build an inverting or non-inverting amplifier. The open loop amplifier has one pole. We will focus first on the constant gain A times K1 with zero phase between input and output voltage, respectively epsilon and Vout. For the vectorial diagram, vectors Vin and Vf are referenced to the 0 volt noted with a red dotted line. For the non-inverting amplifier, Vin is positive and Vf plus epsilon equal Vin. Of course, if the gain A times K1 is high, epsilon will be negligible, so Vin equal Vf, and as Vout equal to Vf, the closed loop gain is equal to 2. For the vectorial diagram, vectors Vi and Vf are referenced to the 0 volt noted with a blue dotted line. For the inverting amplifier, Vin is negative. Vf plus Vin equal epsilon. Of course, if the gain A times K1 is high, epsilon will be negligible, so Vin equal minus Vf, and as Vout equal minus Vf, the closed loop gain is equal to minus 1. Now we will focus when the open loop gain A times K1 equal 1, with a phase of minus 90 degrees. If the gain Vf over epsilon equal 1, this means that K1 times Vout equal epsilon with a minus 90 degree phase. The vectorial diagram becomes as shown in the left red rectangle. We start with the reference vector Vi attached to the 0 volt red dotted line. The vector Vf, which is K1 times Vout, is also attached to this red dotted line, followed by the vector epsilon with 90 degrees angle. To get Vi equal Vf plus epsilon, the Vf phase must be minus 45 degrees and its module 0.7 Vin. The output voltage noted in red is twice Vf. The output voltage is represented in time domain with an amplitude of 1.4 and a phase or delay of 45 degrees, compared to the sinusoidal signal in the left blue box in phase with an amplitude of 2. Now we continue with the inverting amplifier type. The reference vector Vin is attached to the 0 volt blue dotted line with the positive side, so the input voltage on R1 is negative. We remind that K1 Vout equal epsilon, and as K1 equals 0.5, Vout over 2 equal epsilon. The vector K1 times Vout must be also attached to this blue dotted line, and epsilon vector must have a 90-degree angle with K1 Vout. To get Vf plus Vin equal epsilon, the K1 Vout vector phase must be minus 45 degrees. The output voltage noted in red is twice K1 Vout and equal at 0.7 Vin. Now, as the vector Vf is equal and in phase with Vr2, we can finish the vector diagram by doing the sum of vector Vout plus Vr2 plus Vf equal minus Vin. The output voltage is represented in time domain with an amplitude of 0.7 and a phase or delay of 45 degrees compared to the sinusoidal signal in the right blue box in opposite phase with an amplitude of 1. I want to thank you for your attention. On my next Thierry Sicard tutorial number 23, we will analyze the closed-loop transfer function for a non-inverting and inverting amplifier. So see you soon and stay tuned.